In this lecture, we will see about Perceptron algorithm for solving logic gates. The perceptron is an algorithm that signals information from an input layer to an output layer. The figure shows the two inputs perceptron. X1, X2 are input signals, Y is an output signal, W0 is a bias, and W1, W2 are weights. First, before going to solve the logic gates problem in Perceptron, we need to know that the Perceptron algorithm states that prediction of y does equal to 1 if wx plus b greater than or equal to 0 and 0 if wx plus b less than 0. This is an important rule we should follow in Perceptron to solve all kinds of problems. Now I am going to solve a logic gate problems using Perceptron in the next slides. This equation produces output 1 only if the sum of inputs is over thresholds, otherwise it outputs 0. Also, the steps in this method are very similar to how neural networks learn, which is as follows. The first one, initialize weight values and bias. The second one, forward propagate. The third one, check the error. And the fourth one, back propagate and adjust weights and bias. And the last one, repeat for all training examples. Now that we know the steps, let us get up and run. From our knowledge of logic gates, we know that an AND logic table is given by the diagram below. The question is, what are the weights and bias for the AND perceptron? First, we need to understand that the output of an AND gate is 1 only if both inputs are 1. So, the following steps listed previous, let us see one by one. Take row 1 from the AND gate table. From this, W1x1 plus W2x2 plus B, which is the important equation. Initializing W1, W2 as 1 and B as minus 1. Then we get x1 of 1 plus x2 of 1 minus 1. Pausing the first row of the AND logic table, we get, for example, x1 equal to 0, x2 equal to 0, we get 0 plus 0 minus 1 equal to minus 1. From the perceptron rule, if wx plus b less than 0, then it predicts equal to 0, that is output equal to 0. Therefore, this row is correct and no need for back propagation. Next, take a row 2. Pausing x1 equal to 0 and x2 equal to 1. We get 0 plus 1 minus 1 equal to 0. From the perceptron rule, if wx plus b greater than or equal to 0, then y dash equal to 1. This row is incorrect as the output is 0 for the AND gate. So, we want values that will make the combination of x1 equal to 0 and x2 equal to 1 to give the prediction, that is y does a value of 0. If we change b, that is bias, to minus 1.5, we have 0 plus 1 minus 1.5 equal to minus 0.5. From the perceptron rule, this works for both row 1, row 2 and row 3. Next, row 4. Pausing x1 equal to 1 and x2 equal to 1, we get 1 plus 1 minus 1.5 equal to 0.5. Again, from the perceptron rule, this is still valid. Therefore, we can conclude that the model to achieve an AND gate using the perceptron algorithm is x1 plus x2 minus 1.5. The diagram depicts this equation. Second one, OR gate. This is the truth table for OR gate. The question is again, what are the weights and bias for the OR gate perceptron? Take row 1 from this W1 x1 plus W2 x2 plus B. This is the important equation. Initializing W1, W2 as 1 and B as minus 1. We get x1 of 1 plus x2 of 1 minus 1. Passing the first row of the OR logic table, which is x1 equal to 0, x2 equal to 0, we get 0 plus 0 minus 1 equal to minus 1. From the perceptron rule, if wx plus b less than 0, then the prediction, that is y dash equal to 0. Therefore, this row is correct. Next, take row 2, pausing x1 equal to 0 and x2 equal to 1. We get 0 plus 1 minus 1 equal to 0. From the perceptron rule, if wx plus b greater than or equal to 0, then the prediction y dash equal to 1. This row is again correct for both row 1, row 2 and row 3. Then take the row 4, passing x1 equal to 1 and x2 equal to 1, we get 1 plus 1 minus 1 equal to 1. Again, from the perceptron rule, this is still valid, quite easy. Therefore, we conclude that the model to achieve an OR gate using the perceptron algorithm gives x1 plus x2 minus 1. This is the truth table for a NAND gate. From the diagram, the NAND gate is 0 only if both inputs are 1. Take row 1 from the NAND gate table from W1 x1 plus W2 x2 plus B. In this equation, initializing W1 and W2 as 1, B as minus 1, and we get W1 of 1 plus W2 of 1 minus 1. Pausing the first row of the NAND gate logic table, x1 equal to 0, x2 equal to 0, we get 0 plus 0 minus 1, which is equal to minus 1. From the perceptron rule, if Wx plus B less than 0, then the prediction y dash equal to 0. This row is incorrect as the output is 1 for the NAND gate. So we want values that will make input x1 equal to 0 and x2 equal to 0, which give y dash a value of 1. If we change b to 1, we have 0 plus 1 equal to 1. From the perceptron rule, this works. Take the row 2, passing x1 equal to 0, x2 equal to 1, we get 0 plus 1 equal to 2. From the perceptron rule, if wx plus b greater than or equal to 0, then it predicts equal to 1. This row is also correct for both R2 and R3. Now taking the row 4, pausing x1 equal to 1, x2 equal to 1, we get 1 plus 1 equal to 3. This is not the expected output as the output is 0 for an AND combination of x1 equal to 1 and x2 equal to 1. Changing the values of w1 and w2 to minus 1, we get minus 1 plus 1 equal to minus 1. It works. Therefore, we conclude that the model to achieve a NAND gate using the perceptron is minus x1 minus x2 plus 1. This is the truth table for XOR gate, which output 0 for both the input is equal, which means A equal to 0, B equal to 0, which output 0. A equal to 1, B equal to 1 means which output 0. For remaining inputs, it produces the output 1. This is the truth table for XOR gate. Now let us see how to implement XOR gate using perceptron. The Boolean representation of an XOR gate is x1 x2 dash plus x1 dash x2. We first simplify the Boolean expression. We get this the last equation. From this simplified version of Boolean expression, we identified to implement XOR gate. An XOR gate is a combination of OR gate, which is x1 plus x2, and NAND gate minus x1 minus x2 plus 1, and an AND gate x1 plus x2 minus 1.5. So conclude that if you want to implement the XOR gate, so it's nothing but implement OR gate, NAND gate and AND gate into a single network. So we conclude that implementation of XOR gate needed a multi-layer perceptron. From this diagram, the layers are 3 layers. The first layers are input layer, the second layers are hidden layers, and the third layers are output layer. So in conclusion, this is just a custom method of achieving this. There are many other ways and values you could use in order to achieve logic gates using perceptrons. For example, these are the values Here another solutions for the logic gates. This will also work. So thank you for this lecture.